Hi everyone, and welcome to the Chapter 1 review for Geometry. In this, we're going to go through the review questions that you'll find at the end of your book if you're using this particular book right here in the edition that we're using. And I'm just going to go through each question. I recommend that you try all the problems yourself first. That's what you should be doing. You shouldn't just look at this, copy all the answers down, and then go to your class totally unprepared to take a test or something like that. Not how it's going to be the best way to use this for you. You should, again, try all the problems first. Make sure that you know what you're doing, and use this video to help you with the ones you struggle with, or the ones you feel like you could use a little more explanation with. Even if you got the right answer, sometimes it's helpful to have a little bit more explanation. So let's get started. We've got 1 through 3 here, describing a pattern in the sequence of numbers. So by describing this, I'm going to write out an actual sentence. Your teacher may not require that. If you're one of my students, write out a description for me rather than just saying, oh, it's this. So I'm going to write out a description here. I notice that each time from one number to the next, I am adding 7, it looks like. So from this one to this one, add 7. From 19 to 26, same thing, add 7, and so on. So in this one, my description would be each time, something like this, each time add 7. I'll try to write a little neater here. Add 7 to the previous term. And let's take that idea, see if we can find the pattern here for number 2. So it looks like it's plus 2 initially, and then plus 4, and then plus 8, and then plus 16. So let's write that down. It's from here to here, plus 2. This one plus 4. So if you were to give a description of this, plus 8 plus 16, there's different ways you could say this, but I'm going to say each time add I think the simplest way I'm thinking right now to say this is to add the next power of 2, starting with, well, 2 is just 2 to the first, and then 2 to the second, 2 to the third, and so on. So something like that, you can say something like that in your own words. You don't have to have it exactly like that, but that's the idea. And then for number 3, going from 4 to 12, 12 to 36, 36 to 108. Initially you might look at that and not quite be sure, but I noticed the pattern here. 4 times what? This one's times instead of adding something, times 3. And then 12 times 3 gives you 36. 36 times 3 gives you 108, and so on. So this one's actually pretty easy. Each time multiply the previous term, there we go, multiply the previous term by 3. Very good. So now we have something like this where we have to do an actual picture. We have to sketch the next figure in the pattern below. So I see one dot here, and then I see that dot surrounded by 9 new dots here, and then I see that dot surrounded by those same 9 dots from the previous term, and then surrounded by 9 new dots, but it's a little bit wider. So it looks like the number of dots is not changing around the outside. It's going to be 9 around the outside still. So I'm going to have that initial dot. Oops, this is for number 4. That initial dot, and then the 9 dots surrounding that. I'll try to make this picture as nice as I can, freehand sketch here. So they've connected those with, not the prettiest thing ever. There we go. I'll fudge that a little bit there. And then you've got that next one, still contains that. So it still has the 9 dots. It looks like it's the same width from here to here as it is from here to here. So I'm going to try to keep that consistent as I go around here. Why don't I just draw the the square around it first. Hey, that is ugly. Why did that disappear? I don't know why that disappeared. Okay. And there we go. And so we still have those 9 dots here, and they are either at the corners or centrally located at the midpoint of the segments. And so if that pattern continues, it's still going to be 9 dots around the outside. The width stays consistent. It's a little big, but I think you get the point. The width is going to be consistent still, and still going to have those 9 dots. 4 at the corners, and then, am I saying 9 dots this whole time? How many dots is that, Mr. Wagner? That's 8 dots. So 8 dots around, located on each square. So 8, not 9. My bad on that one. But we have, I guess, 9 including that center one. That's, I think, what I was initially thinking with that. So that's what it would look like for number 4. Number 5, this one looks a little tricky. Make a conjecture, so make an educated guess based on the results. A conjecture, in this case, educated guess, that's a hypothesis, you can say that too, but make a conjecture. But it has to actually work in each case too. We aren't just saying this is a guess, it worked for one. We have to check and make sure it actually works for all of these. So what does it seem like is happening here? It seems like I've got 4 consecutive integers multiplied together, then adding 1 to that, and then I'm getting that's equal to the square of something. How is this something? How are these two numbers related to this? Well, this one's a little tricky, but I noticed this. I've got 4 times 7, the first integer times the last integer plus 1 equals 29. Here the first integer times the last integer is 40, and 40 plus 1, that equals 41. Does that continue to hold up here? Does my conjecture continue to work? Does it work here? 6 times 9 plus 1, is that 55? You bet it is. And so my conjecture seems to work here. Making a conjecture now based on the results. I could say something like this. It appears that the following is true. And again, this is in my words. You can say it in your own words as long as it's equivalent to what I'm saying here. So is true for any, it appears I'm saying, because we haven't checked this in all cases, but it seems like this is working out at least for these 3 specific examples. For any 4 consecutive integers, you could start off with n plus 1 would be the next one. You're just adding 1 to that previous number, n plus 2, and n plus 3. So those would be 4 consecutive integers. Put a little colon here. It seems like this is the case. If you take n times n plus 1 times n plus 2 times n plus 3, seems like you get that, plus 1, excuse me. Got to add 1 to that. So that plus 1 is equal to, that's a plus sign there, is equal to the first integer times the last integer. So n times n plus 3, that plus 1, all that squared. So I don't think you'll see one as difficult as that on a test you might be taking, but got to be prepared, right? Got to be ready for anything. So this one, first integer times the last integer plus 1 squared seems to be equal to the 4 integers multiplied together, product of the 4 integers plus 1. Moving on to number 6 then. Show this conjecture, show the conjecture is false by finding a counterexample. The cube of a number is always greater than the number. So you might initially think this is just me kind of brainstorming on this problem. This isn't required in the answer necessarily, but this is some examples. But we're trying to show or find a counterexample. So it seems like if you just think of some random whole number, maybe like 3, and you take 3 cubed, you get 27. Does the conjecture hold true in that case? The cube of a number is always greater than the number. So this is the cube of the number is 27. Greater than the number you started with before you cubed it. Is 27 greater than 3? Sure, so that would work. The conjecture would hold up in that case. If you took a bigger number than that, 5 cubed, that'd be 125. 125 is greater than 5. That holds. That's true. But what would happen if you went a little lower than 3? 2 cubed would be 8, so still holding, but getting closer. The difference between 2 and 8 is only 6, whereas between 3 and 27, that was 24. So a counterexample is where you find a case where the conjecture does not hold, does not actually have to be true, or is not true. So if I took 1 cubed, what would happen? 1 cubed would be, I'm going to say counterexamples. I'm going to show you more than one here. So I don't need the parentheses around that. There we go. So 1 cubed, that would be 1. Now is 1 greater than 1? No. So the cube of a number is, I've just shown it is not always greater than the number. Maybe if you said the cube of an integer where the integer was 2 or more, something like that, then that, yeah, I could see that holding. I do not understand why my equal signs are disappearing when I do stuff like that. Not sure what's going on, but 1 cubed, that would equal 1. If you took 1/2 cubed, you'd have 1/2 times 1/2 times 1/2. That'd be 1 cubed on the top, which is 1, and 2 cubed on the bottom, which is 8. Clearly this is smaller now than the number you started with. You could do that with any fraction that's less than 1, and that would also work. Could you do this with negatives? I'm going to check it out. Let's see. So if I took -3 and cubed it, -3 cubed would be -27. Is this number, -27, is it greater than -3? No, it is less than -3. If you put those on a number line, -27, that'll be much farther to the left than -3. So here's some counterexamples. These were some examples, but counterexamples is what we're looking for. So any one of these three, or any one you come up with, basically any number that's 1 or less than or equal to, is a better way to say that, less than or equal to 1, is going to be a counterexample, it appears. And so let's check out questions 7 through 9 now. For 7, it says draw 5 coplanar points, A, B, C, D, and E, so that ray BA and ray BC are opposite rays. Oh, are you getting confused yet? I hope not. And segment DE intersects line AC at B. So don't try to think of that all at once. Let's just do these things one thing at a time. So let me divide this up a little bit here. And I'm going to go freehand sketch again. This time I'm making my lines a little bigger. I want to see if that disappears less. So when I do the undo button, I'm hoping that things won't disappear if I made the line a little bigger for whatever reason. I don't know why that was happening. Okay, 5 coplanar points. So we've got a plane. I'm going to draw a plane to start. All 5 of those points, A through E, need to be on this plane somewhere. Alright, I'm going to use a different color just to help things stand out a little better here. So that BA and BC are opposite rays. That means they head in the opposite direction of each other, exactly opposite direction. Together, in other words, they form a straight line. So I've got B right here, and I'm going to call this A, and this would go on forever in that direction. If it's an opposite ray, it's got to go in exactly the opposite direction. And then that could be BC. So that makes that true. Alright, so that part's done. BA and BC are opposite rays. DE intersects AC. So here's a line AC. And DE, segment DE, intersects AC at B. And so I could put this segment anywhere as long as it crosses through B and is on this plane. I could put the segment there, anywhere I felt like it, and I'd be okay. So I'm going to call this, it says segment, so I'm going to connect those two. I could draw a line after that. It would still be true that segment DE, if I called this D and I called this E, it would still be true that segment DE, even if I added the little line here, the arrow going on in both directions, this would still be true. Segment DE would still intersect AC at B. So that takes care of both of those requirements. I'm good to go on that one. Let's check out number 8. Sketch 3 planes that do not intersect. Well, there's different ways you could orient this, but the basic gist of it is that it's like you have 3 pieces of paper and they have to be parallel to each other, in other words. So this would be a good quick representation of that. These aren't going to intersect. The planes, remember, go on forever in all directions, but we can't draw that, just like we can't draw a line that goes forever because we don't have forever. Our lives are finite. Even if our lives were infinite, could you draw an infinite line? Could you draw a line that just keeps going? I don't know. Is the universe infinite? Woo! You're blowing my mind, Mr. Wagner. Okay, let's go back to geometry and not get into crazy physics questions right now. Sketch 2 lines that are not coplanar and do not intersect. So 2 lines that are not on the same plane and do not intersect. So I could draw something like this. This is the definition. That is ugly right there. Let's try that again. It's still pretty bad. Straight line, straight line, straight line. Pretend that's a straight line. Okay, so this is the definition of skew lines again. We saw that in this chapter, but skew lines, they are not on the same plane. They don't intersect. So it's like if this was a tightrope. I think we saw that. It's a little hard to visualize this. I'm actually going to draw in a plane. So let's say this line was on this plane. It's hard to visualize it without thinking of it like that. But this would be like a tightrope, and then you've got, I forget his name now, but you had that guy, if he was holding a, what do they call that? I can't even think of that name right now either, but if he was holding something that helped him maintain his balance, the tightrope and that thing he was holding would not intersect. So I'm thinking of it like that. It's hard to draw that in 2 dimensions here on paper to visualize that 3-dimensionally. But let's say it goes underneath here instead. So we're saying that's underneath the plane. These lines are not coplanar and they do not intersect. They don't actually lie on the same plane. Maybe a slightly better way to do this would be to draw it so that it extends on there a little bit more, and then all of a sudden it goes through there. So this is okay, but I think a better way to do that might be more like this. So pretend this line's on this plane, and then maybe you have an arrow shooting straight through the paper vertically, and then it dips down like that, something like that. That might be a little easier way to picture it. So think of an arrow or something shooting through, maybe a laser beam shooting through the paper like that, where this line was on the plane and then this one crossed through the plane but was not on the same plane. Okay, moving on. Hopefully I did not confuse you there. Number 10. All right, we got Q between P and S. R is between Q and S. S is between Q and T. Whoa, so much information here. How are we going to do this, Mr. Wagner? Again, just take it one step at a time. Don't try to do too much at once or try to think of it all at the same time. If we make a mistake, we can adjust our picture. That's why we have erasers. That's why we should use pencil in math class. But we've got PT equal this, QT 16, PQ is the same as QR, is the same as QS. We're supposed to find PQ, ST, and RP. Notice I left a lot of space for this one because there's a lot going on here. This problem gets its own page. So Q is between P and S. So let's start off with that. And if I need to adjust this, I can. So Q between P and S. Between, remember in geometry, means if they're connected with a segment, it has to lie inside of that segment somewhere, not be right on the endpoints of that segment, in between. And it can't be off the segment either. So if Q is between P and S, this would be Q then. This could be P and S. This would be valid. And R is between Q and S, so this could be R right here. S is between Q and T. And so here's Q, here's S, so that means T would have to be on the other side here. Because now this picture is not drawn to scale. I might adjust some stuff here, but here's the general idea of the location of the points. The distance between the points, again, might not be correct scale-wise, but the location of the points relative to each other is correct now here. We got P, Q, R, S, T. Nice that they put them in alphabetical order for us. That wasn't necessarily going to happen until we used information to determine that that had to be true. Alright, so we got PT is equal to 30. I'm going to connect these all with a segment here now. PT is equal to 30. So from here to here, the whole thing is 30. And it says that QS is 16, so from here to here is 16. And it also says that PQ equals QR, so this segment is equal to this segment, which is equal to this segment. So if these three are all equal, it might be a better idea for me to erase this. If I'm going to try to draw it somewhat to scale, I'm going to take this, pare it down a little bit here. So I want this distance to be the same here. I wanted to make that red still. There we go. So we'll call that, oops, I'm pressing the wrong button there. There we go, P. And from here to here, now that looks pretty good. This, again, was equivalent or congruent to this one, which was congruent to this one. So it seems to me that now that we've got the information labeled correctly, this is actually going to be a pretty easy problem, because if I know that Q to S, if I know that's 16, and I know that this is congruent to this, I know that this has to be 8, and this has to be 8. They're congruent, they have to be the same. 8 plus 8, 8 times 2, in other words, equals 16. If this is 8 and this is 8, this has to be 8 as well, since they're all congruent, all three of those. And then if you take these three together, you've got 24. And if you do 30 minus 24, that gives you 6. Therefore, ST, what's left over, since 24 is from here to here, you'd have to have 6 more from here to there to get the whole distance of 30. So now what's PQ? Looking at the picture, PQ clearly is 8. What's ST? Looking at the picture, that's clearly 6. And what is RP? Looking at the picture, once again, this would have to be 8 plus 8, which is 16. So there are your answers based on the picture. Once we determined where the things went, where the points correctly were, then the rest fell into place pretty easily. Let's move on to number 11. Alright, we're going to use the distance formula to find or determine, to decide whether PQ is congruent to QR. So since it says to use the distance formula, we're going to do that here. There are different ways to approach a problem like this. Using the Pythagorean Theorem is, I think, one of the best alternative methods, at least, to figure this out. But we'll use the distance formula. I'll briefly explain how you could use the Pythagorean Theorem to figure these things out as well. But again, I hope you're using this for test preparation. If you're trying the problems first like you should be and not getting it, then you're using this to help you to get ready to show what you know on a test or a quiz or something like that. So PQ, is it congruent to QR? So the distance formula was this again. It's the difference of the x values squared plus the difference in the y values squared. It's the square root of all of that. And so let's take our points here, P, Q, and R. I'm going to call the values here for P. Initially, I'm going to call this x1 and y1 for my first x coordinate and my first y coordinate. And then for Q, I'm going to write over the R points right now, since we're not really concerned about those at this point. I'm going to call this x2 and y2. And so I just need to label them correctly and then plug them into the formula correctly, and I'll be able to see what I've got here. That was a pretty straight line. Not bad, Mr. Wagner. Not bad at all. We've got 1, Well, let's start with our x value, sorry. We've got -2 for my x2, and then it's minus -1, so it's minus the -4. And we're squaring that. It's the difference of the x values squared plus the difference of the y values squared. So we've got 1 minus 3. We're squaring that. What's this going to equal? This is going to equal, we've got -2. This would change to +4. So that would be 2 squared. And I'm sorry, I should label this as PQ. So this is PQ. PQ is equal to this. And we've got this plus, this would be -2 squared. The negatives will go away when you square them. So we've got the square root of 4 plus 4. That is the square root of 8. Now we could do simplified radical form. But if we can just show that this equals the square root of 8 down there as well, we really don't need to. I think I'll leave that out for now, but you should know how to do simplified radical form. You should know how to do something like this. If you don't, you might want to find some videos to help you out to review that online, or ask your teacher about it, ask me about it if you're in my class. But this would be the same thing as 4 times 2. You could pull out the square root of 4 as a 2. So that would be the same thing as 2 radical 2. But from here, let's find out what QR is and determine if they are in fact congruent. So now I'm going to go back up here, erase this stuff, and yeah, why don't I use blue this time around? Just for fun, just for kicks. And I'm going to go with QR now. QR is equal to, now I'm not using P, so I'm going to write over that. This is x1, y1, the -2 and the 1. And then R is x2, y2, my second x coordinate, my second y coordinate. Still using the formula. I'm taking the difference of the x values and squaring that, 0 minus -2, plus difference in the y values squared, so -1 minus 1. That would be, this is looking promising, 2 squared plus -2 squared looks like exactly the same thing as I had before. So yes, I would get that these are in fact congruent. Now we've used the distance formula to determine this. So this is square root of 8. You can do the same thing here. And so based on this fact that you have this and this being the same, I'll circle this, I'll circle this. Are they congruent? You can say with certainty yes, that PQ is congruent to QR based on what we did there. Okay, so I said we could use the Pythagorean Theorem as well to determine this. I think, oh boy, I'm just running out of room here. So I think, why don't I just add a blank page to this. No, that's not how we do it. There we go. Insert page after this one. So if you wanted to use Pythagorean Theorem, graphing it's helpful, I think, to help you visualize why this works. But let me erase this here and here. So I'm going to plot these 3 points. -4, 3 is P. So let's go 1, 2, 3, 4, 5 in each direction. Trying to make my scale as nice as possible with a freehand sketch at least. And so -4, 3 I believe it was. Is that correct? Yes, -4, 3. So -4 and +3 right here. This was P. -2, 1. That'd be right here. -2, 1. That would be Q. And 0, -1. 0, -1 would be R. Alright, so using a picture like this, we can use the Pythagorean Theorem by figuring out how long things are from drawing right triangles. So from here to here and here to here, I can connect these and make two right triangles. This one's 2 from here to here because I'm going from -3 to -1. I'm sorry, from +3 to +1. That's what I mean to say there. So those were the difference. Notice the difference in my y values. That's what I have right here. The difference in my y values is 2. The same thing happens here. The difference in my y values going from q at 1 to r at -1. The difference in my y values is also 2 from q to r. And so that goes in right here. The difference in my x values, I'm going from -4 to -2 for q. So the difference between these two is also 2. And the same thing here. I'm going from -2 to 0. That's the difference in my x value. So notice, using Pythagorean Theorem, I've got PQ is equal to 2 squared plus 2 squared, the square root of that, because PQ squared would equal 2 squared plus 2 squared. Pythagorean Theorem says the hypotenuse equals the two legs, the sum of the two legs squared. So if you took the square root here and here, this would cancel out. You'd have PQ equal to that, which is the same thing as what I ended up getting over here. So you could use a Pythagorean Theorem to determine this as well. You wouldn't even have to draw it out. You could just find the difference of the y values right here. That's from 3 to 1, that's 2, and square it. And you could find the difference in the x values right here from -4 to -2. That's also 2, and square it. And then just take the square root of both of those added together. So that's another way to think of the distance formula. I actually prefer thinking of it that way myself. But if you know the distance formula, you like it. If you're good with just using formulas and plugging in the numbers from algebra, go ahead and do that too. So I'm not going to talk about Pythagorean Theorem again and how it relates to the problems here with the other two, just because I feel like that's unnecessary. This would work as well, remember, for QR, because it's the same. It's 2 squared, it's 2 squared. But let's move on to these other two. Use the distance formula to work these two out. So we've got, I'm not going to label them this time, just to save a little time here. I'm just going to use the formula, call this x1, call this x2 in my mind. But if you want to label them, if that helps you, go ahead and do that. So I've got 1 minus -3 squared plus, and this was my second coordinate, so I'm using that one first. I got to keep that consistent. As long as I'm consistent, it'll turn out okay. And 3 minus 5. So this one minus this one squared, this one minus this one squared. It's going to end up being, this would be 4 squared, because that will change to plus 3. And this would be -2 squared. That'd be 16. Come on, there we go. Plus 8. So you'd have the square root of 24. Again, we could do this sort of thing if we wanted to, or if your teacher was requiring you to show that here. This one, perfect square that goes into 24. The biggest one is 4. So you'd have 4 times 6. You could pull out the 4 as a 2. So this is the same thing as 2 radical 6 if you had to show that in simplified radical form. Excuse me. Let's go blue again for QR. QR is going to equal difference in x values minus difference in x values squared minus plus, the difference in y values squared. Might need to take a little voice break here. My voice is starting to go. But I've got difference in the x's squared, 4 minus 1 squared, and then difference in the y squared. As long as I start with the same one I started here, I'm okay. So I've got 1 minus 3 squared. So this is not looking good to me because this is a different number right here, 3 squared. This is still -2 right here, but this is going to be different. So this will be the square root of 9 plus 4, which is the square root of 13. You can't use simplified radical form on that one. Since these are different, are these congruent? we look at this, we look at this, not the same, so we would say no, that PQ, we could draw it like this and draw a slash to that, is not congruent to QR, segment PQ not congruent to segment QR. And then finally for number 13, same idea, same process. PQ, square root of the difference of the x values squared, 0 minus -2 squared. And the difference of the y values squared would be 1 minus -2 squared. Let's see what that gives us. That yields, this would be 0 plus 2, which would be 2. So you'd have 2 squared for the x values. And then for the y values, you would have 1 plus 2 would be what that changes to. You'd have 3. So this looks like you've got the 4 and the 9 again, so you get the square root of 13. There's no perfect square that goes evenly into 13. And so that would be simplified radical form as it is in this case. And then QR, going with my blue again, is we're going to have difference of x values is 1 minus 0, we're squaring that, and then the difference in the y values is 4 minus 1. So this one, squaring that, it looks like we're going to have 1 squared for this first one and 3 squared for this other one. That is square root of 1 plus 9, which equals 10. So the square root of 10, square root of 13, we look at this, we look at this. They are not the same, therefore we say no. In this case, once again, PQ is not congruent to QR. So, yeah, I'm glad that's over. That's a lot of work, but that's okay. And now I think we're moving on to some easier ones to do here. So classify the angle as acute, right, obtuse, or straight. Or at least some quicker ones, not easier necessarily, but at least quicker. Sketch the angle, then use a protractor to check your results. I have, in fact, on here a protractor, so I'm excited to use that. That'll be fun. There it is. I was like, I don't remember where it is. But I'll move that down here, so you should get a protractor to check your results as well. 180, that's the definition of a straight angle. So for number 14, this is a straight angle. And so if I were to draw a straight angle, I would still need a point, a vertex, and then it would go out from the vertex, but it needs to be a straight line. So, hey, not too bad there for a freehand sketch. I'm going to move this now, use this to check my results. Yeah, that's pretty good, especially for a freehand sketch. So if you have a ruler, you could use a ruler. That'd be a helpful thing. I've got my straight edge tool, so I guess I could have used one of those and just did something like this. But this is good. I got it. I got what I need. So number 15, let's check that one out. 15. Anything between 90 and 180, that's the definition of obtuse. And so for this one, we've got an obtuse angle. So sketch the angle. I'll use my straight line tools. Why not? So I'm going to try to sketch one that is actually, I want to use red just because I have been. So 150. 90 would be like that. Pretty close to that. So I want to change one of these. I want to adjust it. No, I can't adjust it like that. I can spin it. There we go. So I'm going to adjust it so that it's a little more than halfway. I'm going to move this over, and I'm feeling like that's pretty close to 150. I'm going to use my protractor to check that. See how close I got here. So I need to line that up. Oh man, that was money. So 150 right there from 0, and then this goes to the 150 here. If it's bigger than 90, we use the bigger number. Hopefully that's clear to you. So that's not 30, but it's 150 instead. And so I would add some arrows to the end of those, and this would be 150 degrees right here. This one would have been 180 degrees. And then the measure of angle y. So I should be including some points here as well. Sorry about that. So KLM, L has to be the vertex since it's the middle point. And then K and M could be in either location. This was a measure of angle A, so this would have to be point A as my vertex. And then for 45 degrees, that's the definition of acute right there, if you have something between 0 and 90. And so I'm going to get out my tools again. And if I think back to 90 degrees like that, once again, that'd be a right angle. I'm trying to adjust this so that it's half of that angle. So let's see how I did there. I'm feeling like that's pretty close to 45. Gotta adjust this a little bit. Not quite as good as the last time. Okay, so I need to move. Notice this is on 40 degrees right now, so I need to move this slightly up here. If I can get the protractor out of the way, there I go. So let's try that now instead. You might be asking yourself, wouldn't it be easier to just draw a 45 degree angle to start? Yeah, probably. Okay, but they're saying sketch the angle, then use a protractor. So I'm trying to follow the instructions they give me. I'm trying to follow what they say to do. So that seems pretty good. If anything, I could just change that just ever so slightly this direction. Okay, let's check that out now. Move it or lose it, sister. Okay, here is... No, I adjusted it too much. But anyway, I hope you're getting the point. Did I... Did I get it? Did I get it? I feel like that's pretty close. I still need to move it just a little bit, but I move it just a little bit. Okay, that's going to be okay now. It should be okay now. Yeah, feeling pretty good about that now. Right halfway in between there, 45 degrees. So this is the measure of angle y, so I need to put a y there. I'll put some arrows showing that it goes on forever, and this would be 45 degrees right there. We didn't answer the question yet. This is acute, so I think I verbally said that, but I didn't write it down. So straight, obtuse, and acute for those ones. So let's check out the next batch. And we don't need a protractor for this, so farewell protractor here. It says use the angle addition postulate. Remember the angle addition postulate. Hopefully you remember what that says. It just says that if you have two angles that are adjacent, meaning they share a common side, a common ray like these two do, like these two do, like these two do, you can just add the measures together to get the whole angle, to get the big angle. So let's use the angle addition postulate to find the measure of the unknown angles here. So on this one, the unknown angle, well, we know DEG is 60. We know GEF is 45. The unknown angle would be DEF, the big one. So the measure of angle DEF would be 60 plus 45. That'll be good enough for what we're doing here. So the measure of angle DEF is 105 degrees. On this one, we're given the big angle. HJK is 90. We're given a smaller angle here. LJK is 40, and we're missing this one right here. So what's the measure of HJL, or LJH is another way to say that one. Measure of that one, measure of HJL would be the 90, the big angle, minus the smaller angle. It's going to leave us with 50 degrees for the measure of angle HJL. And then finally on this one, the measure of angle QNM. Well, you might look at this one and say, they only gave us one piece of information. How can I figure out the other things there? Well, based on the fact that this is a straight line, we can see that looking at the picture. We can assume then that the measure of MNP or PNM, it's So another way you could say that, we can assume that that's 180. So we're looking for the measure of this one, QNM, based on that. So the measure of angle QNM, you could also say, how else could you say it? You could say M and Q, as long as N, the vertex, is in the middle. You've got 180 minus 110. So the measure of angle QNM, the unknown one here, is 70 degrees. Continuing on with life and with math and with fun problems here, we got the coordinates of the midpoint of a segment with the given endpoints. So I am, use that one instead. I'm just going to split this up into 3 parts again. And so we're going to use, it looks like, for finding the midpoint, we can use that midpoint formula that we learned about. So we just take the two, we take the 2 points that were given. We find halfway in between the x values and halfway in between the y values. That's going to be our midpoint. So the midpoint formula, again, tells us that we do this. We do x1 plus x2 and divide it by 2. That's halfway. The average of the x values is another way to say that. We do y1 plus y2. So take the 2 y coordinates and divide it by 2. That's your midpoint. And so for here we would have the x values, 0 plus -8 divided by 2. That would be the same as 0 minus 8. And my y value is 0 plus 6. Finding the average of the y values. And so this would be -8 divided by 2, which would be -4. This one you'd have 0 plus 6, which is 6, over 3, or over 2, which is 3. If it helps you do that intermediate step, why don't I write that in here? Some of you might be wondering where that came from and didn't follow mentally what I was saying there. So this would be -8 over 2. This would be 6 over 2. So that equals -4. That equals 3. So that would be the midpoint. If you were to draw these points on a coordinate plane, you would see that, in fact, I'll do that real quick here for this first one just to help you visualize what's going on. That was a little too big that way. So 0, 0, -8, 6. If I went -8, 6, it'd be in the second quadrant, so I could be successful like this. Successfully draw both points on a graph like this. So 0, 0 would be right here. That'd be point A. If I went back 1, 2, 3, 4, 5, 6, 7, 8, and up 1, 2, 3, 4, 5, 6. Trying the best I can with the freehand quick sketch here just to show you how to do this. You don't have to draw this yourself. This is just to help you understand why things are the way they are. So this is -8, 6 right here. This is 0, 0 right here. Does it seem like this is the midpoint? If you went -4 and 3, does it lie on the segment and is it halfway in between A and B? Seems like we got it right on the money there. So -4, 3 looks like the midpoint. That was halfway between the x values, -8 and 0. -4 is halfway in between there. Halfway in between the y values as well. 6 and 0, 3 is halfway there. So this just helps you visualize what's going on. I won't draw the graph for these other two, but you could if you wanted to. If you prefer to do it that way and to think of it that way, go ahead and do that. 21 though, same thing. Take your x values, put them together, -1 plus 3, and divide by 2. Find the average, find halfway in between the x values like that, and then do the same thing with the y values. 7 plus -3, divide that by 2. You've got 2 over 2 for the first one. You've got 4 over 2 for the second one. That is the same thing as 1, comma, 2. So this one, that's the midpoint for segment JK. And no, I am not JK. You're so funny, Mr. Wagner. I almost forgot to laugh. Okay. We've got negative 12 and 2. Add them together. Divide by 2. That's the average of the x values there. And then negative 9 plus 10 over 2. That's the average of the y values. You've got negative 10 over 2. You've got 1 over 2. That is negative 5. And then you can have a fraction that happens sometimes. 1/2 would be your y value for the midpoint. Let's move on to 23 through 25 here. QS, it says, is the bisector. That means it cuts it in half. Cuts the angle in half of PQR. So it cuts in half. Find any angle measures not given in the diagram. So it appears there's the two smaller ones, and then we got to think about the big one as well. So let's get out my line tool there. Let's split this up. Three different parts. Okay, good to go. 23. If it's a bisector, and this is 50, that means that has to be 50 as well. So we can clearly say the measure of SQR is going to equal 50 degrees. And then the big one, PQR, would have to be 50 plus 50. In other words, 50 times 2, which is 100 degrees. Number 24, this time it gives us the big one. That's why they drew in the whole arc like that, to say that the measure of RQP is 50. My headphones are squeaking. My microphone's squeaking. I hope you can't hear that on the video. I'll try to stop that. Okay, so the measure of PQS would be this one. That'd be 25. It'd be half of 50. And the same thing about this angle right here. That would be SQR once again, or RQS would be another way to say that. So PQS 25. RQS, other small one, also 25. Beautiful. Moving on, 25. This time they give us a smaller one. Again, it's the bisector, so that one's got to be 46 as well. It looks more like a 9. Let me make that look a little better. 46. And so we've got the measure of angle SQR once again. It's 46 degrees. The measure of angle PQR would be 46 times 2, or in other words, 92 degrees. Alright, we're almost there. Just a couple more batches to go here. Use the diagram above to decide whether this statement is always, sometimes, or never true. Where is the diagram above, Mr. Wagner? I don't know. Let me go find it just a second. There's my missing diagram. So use the diagram above or to the right here is where we have it to decide whether the statement is always, sometimes, or never true. So 26. I'm going to label some things over here. If the measure of angle 2 is 115, then the measure of angle 3, would that have to be 65? Well, yes, because this is a straight angle right here. These two have to add to 180. 115 plus 65 would in fact be 180. So is this sometimes, always, never true? This is always true. .27. Let me erase what I had there. Now I've got a new set of requirements or data. We've got angle 3 and angle 4 are congruent. So if this one, let me use blue just to make that stand out a little better. If this one was congruent to this one, is this always, just based on what's in the picture here, does this always have to be true? Do they always have to be congruent? Well, no, this could be 45 and 45, but this angle, this line could be more at an angle like that. It could be more at an angle like that, really steeply sloped there. So these wouldn't have to necessarily be congruent based on the picture alone. We wouldn't say that has to be true. Could it be true? Yeah, it could be true. So that would be a sometimes. (28). How about this one? If the measure of angle 1 is 40, then the measure of angle 3, would that have to be 50? Well, look at these two angles. These are vertical angles. Vertical angles are always congruent. So if this is 40, it's not possible. That would also have to be 40. You can't have two vertical angles that have different measurements. So this one would be our first never. And keep pressing that button on the pen I'm using to write. That's why it's not writing. Number 29, 1 and 4 are complements. 1 and 4 are complements. So this one right here, use blue again, there we go. This one right here and this one right here, 1 and 4. These have to, in other words, if they're complements, they have to add to 90 degrees. Does that have to be true? Well, seeing that this is 90 degrees right here, that's what the box means in the corner, and seeing that 1 and then this angle, the right angle, and 4 all together form a straight line, the only way for that to happen is if 1 and 4 add to 90, because 1 plus 4, if that's 90 and this is 90, then you have that straight angle, then you have 180 degrees. If 1 and 4 did not add to 90, you would not have a straight line right here. So this would always have to be true as well. Looking at the answers in the back of the book, it said for number 29, sometimes. I'm just going to have to agree to disagree on this one, because I don't see how they could say sometimes. If this is a straight line, which looking at the picture, clearly that looks like a straight line to me. If they're saying that has to be a straight line, then these would have to be complements. These would have to add to 90. So I'm not sure where they came up with sometimes. Maybe they're assuming this doesn't have to be a straight line, but then that throws everything else off too. So I don't like their answer. I'm going with always. I'm saying this and this 1 and 4 always have to add up to 90. They always have to be complements. But other than that, the rest looked okay to me. And then finally, our last batch of questions here, 30 through 33. Find the perimeter or circumference and area of the figure described. I'm going to draw in some stuff here just to make it a little easier to keep things clear. I've got a rectangle now. I'm going to draw pictures for each one of these as best I can. I'm just going to go freehand. So hopefully you understand that these are supposed to be perfectly parallel and perfectly perpendicular to each other as well, even if it doesn't look like it. So 10 centimeters for the length and 4.5 centimeters for the width. There's a triangle where that is the case. And so what's the perimeter? Perimeter, remember, you add up all the sides. Think about walking around the perimeter of a building. You would just walk around the outside of a building. Same thing holds true here. So you could do 10 times 2 plus 4.5 times 2, or you could just write 10 twice, add them together, and you could write 4.5 twice. Either way is going to do the job for you here. This would be 20. 4.5 times 2 would be 9. So you've got 29 centimeters for the perimeter of a rectangle like that. 31, if you had a circle with a radius of 9 inches. And it says to use pi as 3.14. Therefore, I'm going to plug it in into a calculator as 3.14 and not use the pi button on my calculator. I think using the pi button generally is a better answer. I know it is a better answer, but if it says to use 3.4, that's what we're going to do. So find the perimeter or circumference. Circumference is the perimeter of a circle. So it's walking around the outside of the circle. It's finding the length of the outside of the circle. We've got circumference. is the fancy name for the perimeter of a circle. So we've got pi 2 pi r for this. We know the radius is 9, and we're supposed to use pi as 3.1. I don't want to do that. There we go. So I'm going to write in 3.1. I'm going to make this approximately equal to now, since it's approximately 3.1 for pi. And I've got 9. If I use my calculator to figure this out, I've got 2 times 3.14 times 9 gives me 56.52. And this was in inches, so don't forget your units. Number 32. Okay, this one we have to draw a graph. We've got -6, 0, so that'd be in this. It's on the border of the second and third quadrant. -2, -3, and 2, 0. So I'm going to draw a graph like this. Will do that pretty well for us. Get all 3 of those points in there. Notice I'm doing this freehand. If you're going to do this freehand, you just got to be really careful with your scale. Graph paper is advised. If I were your teacher giving you a test, I would have the graph lines on there properly drawn in for you, but this should do it for us as long as we make a careful graph. So 0 or -6, 0 would be 1, 2, 3, 4, 5, 6. Just double check that. This would be point A. -6, 0. 2, 0 be 2 and up or down none. That would be at point B. And then -2, -3. This would be point C. And so a triangle defined by that. I might have to use an extra piece of paper for this one, because I'm going to have to find out what's this right here. These links on a diagonal. Alright, so I know that C goes down to -3. It's going from 0 to -3. So I know this is a value of 3 from right there to right there. I know AB would be, this is going to -6. This is going to 2 in this direction. So that's a total of 8 from there to there. I'm trying to find the perimeter of this triangle, so I need to add these 3 sides together. However, it appears that this one, I don't know the diagonals. I have to do some extra work for that. So I'm going to have to use Pythagorean Theorem to figure that out here. So 1, 2, 3, 4 is from here to here. And then here to here is also 1, 2, 3, 4. And so both of these are actually congruent triangles. This was not a perfect drawing, so it doesn't look like it. But that means if I just look at this particular part, or this particular right triangle, if I did 3 squared plus 4 squared, that would have to equal AC squared. And if I took then the square root of both sides, that would get the square root and the square to cancel there. I would have the square root of 9 plus 16. This happens to be a nice perfect square. Here the square root and square canceled out. So I've just got AC is the square root of 25, which is 5. So I've got a 3, 4, 5 right triangle here, and the same thing is true over here. This is going to be 5 as well. Now that I have those numbers, I've got 8, I've got 5, and I've got 5. I can just add those 3 numbers together to get my final perimeter. My perimeter is going to be 5 plus 5 plus 8, which is 10 plus 8, which is 18. This one did not have units, so you can leave the units off, or you could write the word units after it. 33, the final problem. The final countdown. The square garden has sides of length 14. What is its perimeter? This is a much easier problem than the last one. The side lengths are 14 feet. Each one is 14 feet. We know they're all the same. The perimeter, since it's a square, we know they're all the same. The perimeter would have to be 4 times 14. And 4 times 14, that is 56. So this would be 56 feet for number 33. And so what did I just do? I did everything right, but what did I just do? It says find the perimeter. This is why you read the directions carefully. And area. So thought I was done. Hold on, not done yet. But I'm close. I've got all the dirty work done, you could say. The tough stuff is done. So the area of a rectangle is just base times height. So I just do 10 times 4.5. That would be 45 centimeters squared. Over here, the area of a circle is pi r squared. Since we're using pi as 3.14, plug in that, and I'd plug in 9. Square that. Use a calculator to figure that out. I've got 3.14 times 9 squared is 81, so I'll just type it in like that. So it would be 254.34. And that would be inches squared. Over here, I know that area is 1/2 base times height for a triangle. So I've got 1/2. The base, I could say, is this part, and the height would be a part perpendicular to one of those sides. It would be this 3 part. So I've got 1/2 of 8 times 3. Be 1/2 of 24, which is 12. And no units given, so I can just leave that off. Or I could write units squared. And then finally over here, the area of the square would be 14 squared. It's just side squared. And I know 14 squared is 196. So I've got 196 feet squared. All my units, when I'm talking about area, remember, is always units squared. So my friends, that should do it for us. That is all 33 problems here in the Chapter 1 review. I hope you found it helpful. Hope you found it insightful as you prepare for your tests, and I hope you tried them again yourself first. I hope you listened to my instructions there and just use this as an additional tool to help you in preparation for your test or your quiz coming up shortly. All right, have a good day, everybody. Glad you could join me here on Wagner Academy for the Chapter 1 review for geometry. Good luck. Go get them. Study hard. I'll see you later.